All right, in this video, we're going to quickly look over how to name acids for introductory chemistry, so acid nomenclature. To begin with, just a quick definition of an acid. Acids are substances, chemicals, that will increase the concentration of hydrogen ions when they're placed in water. So they produce hydrogen cations in water. So because of that, acids will almost always have hydrogen at the start of their formula. There are a few exceptions to that, as you'll see in just a moment, but usually if you see a compound with hydrogen at the start of the formula, that is an acid. Of course, one very common exception to that would be water, H2O. Now, as you'll learn later in chemistry, water does have acid and base properties, but it's not named as an acid. Another exception to that would be hydrogen peroxide, where that is also not named as an acid. But those are two common exceptions, but basically, other than those, when you see hydrogen at the beginning of a formula, you should be thinking that it's an acid. So some examples, HCl, aqueous, AQ means dissolved in water, aqueous, H2S, HNO3, H3PO4. You notice all of those formulas begin with hydrogen. So therefore the clue is that those are acids. The aqueous is there because the definition of acids was referring to the fact that they produce hydrogen ions in water. For the more complicated formulas like HNO3 and H3PO4, you'll often see the aqueous just left off. For the simpler formulas like HCl and H2S, usually you do need to see aqueous beside it. If you saw gas, for example, HCl gas, the nomenclature would be a little bit different. Now, some acids are referred to as carboxylic acids. They're a type of organic acid. We'll study them in more depth when we get to the organic chemistry unit later in the course. But a carboxylic acid will have what's called a carboxyl group in its chemical formula. A carboxyl group looks like this, COOH, and it'll usually appear at the end of the chemical formula. So here are two examples, CH3, and then you see COOH, C6H5, and COOH. So that COOH is a carboxyl group, and therefore these two things are carboxylic acids. In the carboxylic acid, the hydrogen that makes it an acid is at the end of the formula rather than at the beginning. Now, there are two broad categories of acids. Acids can be considered binary acids if the hydrogen ion is attached to a simple ion. In other words, these acids will have only two elements, which is why they're called binary in their formulas. Here are some examples. H with Cl, so only two elements, and that's called hydrochloric acid when it's dissolved in water, and we see the aqueous there. H2S, again dissolved in water, is hydrosulfuric acid, and HI is hydroiodic acid. Now you might wonder why the first and third of those formulas had only one hydrogen in the formula, while the second one had two. That's looking at the charges of those other elements. So Cl is Cl minus, I is I minus, so therefore those two ions would receive just one hydrogen ion. So you get HCl and HI. The hydrogens are positive, right? The middle example has a sulfide anion, which is S2 minus. Because it's 2 minus, sulfide gets two hydrogens attached. H2S is its formula. Now, when you look at the three names, you see that they all have some commonalities. They all begin with the prefix hydro. So if you have a binary acid, you're going to see hydro at the beginning of its name. Then there's some kind of root, and then there's the suffix ic, and then a separate word, acid. So binary acids will always be named like this, hydro something ic acid. So HCl was hydrochloric acid, H2S was hydrosulfuric acid, and HI is hydroiodic acid. All right, we'll look at some more examples later on. The second broad category of acid is called an oxyacid. It's called that because you'll see oxygen in its formula. But what I prefer to think about is here you're going to have hydrogen bonded to a complex ion. And the complex ion is the thing that'll have oxygen in its formula. Now, complex ions or polyatomic ions generally have one of two suffixes. So, for example, you might have nitrate, NO3 minus, so nitrate ends in ATE, or related to that is nitrite, NO2 minus, which ends in ITE. So we're going to have two different sets of rules for when the complex ion in these oxyacids ends in ate, or when the complex ion name ends in ite. So let's look at some examples. So first of all, complex ions where the name ends in ate. So if you know the ions here, you can say their names. Otherwise, you might want to pause and look up their names. So NO3 minus, well, that's the nitrate ion. SO4 minus, that's the sulfate ion. Then we have the chromate ion, the arsenate ion, and then the perbromate ion, BrO4 minus. Now look at the charges on those ions. Nitrate has a charge of just negative, or 1 negative. So if we put hydrogens with that, the formula would be HNO3. It gets 1 hydrogen because, again, hydrogen is just H positive. Sulfate, SO4 minus, gets 2 hydrogens, so H2SO4. The chromate gets 2 hydrogens. The arsenate gets 3 hydrogens, H3ASO4. And then the perbromate gets only 1 hydrogen, HBrO4. Now look closely at the names. When you had the nitrate ion, the acid that's formed is called nitric acid. When you had the sulfate ion, the acid name is sulfuric acid. Chromate produced chromic acid. Arsenate produced arsenic acid. And perbromate produced perbromic acid. Do you see a pattern in those names? Well, you notice none of them start with hydro. The prefix hydro was used only for binary acids. So these acids have the basic property that their names will be something and then ic and then acid. Something, ic, acid. So nitrate, nitric acid. Sulfate, sulfuric acid. Chromate, chromic acid, etc. Okay? If the complex ion named ended in ite, things will be just a little bit different. So here we have 4 examples. NO2 minus is nitrite. SO3 minus, sulfite. IO minus is the hypoiodite. And PO3 minus is phosphite. So now the acid formulas, if the charge is 1 minus, you put 1 hydrogen with it. If the charge is 2 minus, you put 2 hydrogens with it. If the charge was 3 minus, you put 3 hydrogens with it. And look at the names. None of the names begin with hydro, because again, hydro is only used for binary acids. These names, though, their names all end in us instead of ic, acid. So when you had nitrite, you end with the name nitrous acid. Sulfite becomes sulfurous acid. IO minus was the hypoiodite, so therefore this is hypoiodous acid. And phosphite becomes phosphorus acid. So here you see the pattern is something us acid. These two suffixes, ic and us, may sound familiar. We used them back when we looked at the type 2 cations with more than one charge, the older way of naming them. So for example, Fe3 plus could have been called ferric, while Fe2 plus could have been called ferrous in the older way of naming them. So the ic suffix was used for the higher charge, and the us suffix was used for the lower charge. Well, here we have something similar, not exactly the same, but similar. The nitrate ion has a greater amount of oxygen, 3 oxygens, than the nitrite, which has only 2 oxygens. So where you have the greater amount of oxygen, the ion that ends in ate, you use the ic suffix. When you have the lower amount of oxygen, the ion that ends in ite, you use the us acid suffix. All right? So here are some examples. Let's work through them together. So when you see the first example, we're going to try to name it. The first thing that you should notice is that it has hydrogen at the beginning of its formula, which tells you it's an acid. This is almost certainly an acid. Next thing you'd want to notice is that there are only 2 elements in the formula, H and F. Since there's only 2 elements, this is a binary acid. There's no complex ion in that formula. If it's a binary acid, the name will begin with hydro. So we'll say hydro, and then we look and see fluoride was in that formula, HF, so the name will become hydrofluoric acid. So binary acids have that pattern, hydro something ic acid. The next example will work backwards. So we see clearly it's an acid. The name says oxalic acid. So we know the formula will likely start with hydrogens. Oxalic, so there's no hydro at the beginning, which means this is not a binary acid. It must have a complex ion in its formula. If its name is oxalic acid, so it ends in IC, then the complex ion's name must have been oxalate, right? The ate ending produces the ic suffix in the acid name. So now what is oxalate? Well, we look up in our data booklet if we have to. Oxalate is C2O4 and its charge is 2 minus. That's oxalate. So when we write the acid formula, we'll add 2 hydrogens to that, and we get H2C2O4. All right? If it's a binary acid like HF, you should put AQ beside it, aqueous, dissolved in water. If you leave that off, I'll probably be fine with that, but technically it should have aqueous. The acids with complex ions, there's less stickiness about that, so we don't usually require that the aqueous be present. All right, the next example, C6H5COOH. Well, I don't see hydrogen at the beginning of the formula, but I see this COOH, which I recall is the carboxyl group. So this is the organic acid. So then what I want to focus on is that entire beginning part of the formula, C6H5COO. So clearly this is not a binary acid because it's got more than 2 elements. And C6H5COO is a complex ion. C6H5COO minus is on my list of complex ions. Its name is benzoate. Benzoate. So if the complex ion name ends in ate, then the acid name becomes benzoic acid or benzoic acid. The next example, again, we see it starts with hydrogen at the beginning of the formula, which is a clue that it's an acid. It's not a binary acid because I see there's a complex ion attached to it. MnO4 minus is a complex ion. So the name of this acid will not start with hydro. The complex ion here is permanganate. permanganate. So just like the last example, the acid suffix will be the IC, the ic suffix. So this becomes permanganic or permanganic, depending how you want to say it, permanganic acid. The complex ion there was permanganate, so permanganic acid. The next example, Chloris Acid. So there's no hydro in that name, so there must be a complex ion. It's not a binary acid. Chlorus, so then the complex ion must have been chlorite. Chlorite would have been the complex ion. If the acid has OUS, the complex ion must have had ITE. So chlorite is ClO2 negative. That's chlorite. So Chloris acid gets one hydrogen attached, HClO2. And there we have it. One last example, hydrocelenic acid. So here we see the prefix hydro again. So hydro tells me it's a binary acid, which means we have hydrogen attached to just one other element. There's no complex ion here. So selenic, well, that reminds me of selenium or selenium. I look up on my periodic table, because this is not a complex ion, Se is in the same family on the periodic table as oxygen and sulfur, so its charge will be 2-. If we have hydrogens attached to this, we'll put 2 of them and we'll get H2Se. So it's a binary acid. If it's a binary acid, we probably should write AQ, aqueous, beside it as well. So there you have it, acid nomenclature. We have binary acids, hydrogen with just one other element, a simple ion, and the names always have the form hydro something ic acid. And then we have oxyacids where complex ions are present. If the complex ion ends in ate, the name ends in ate, then the acid name has ic in it. So nitric acid, sulfuric acid, etc. If the complex ion name ended in ite, then the acid name has the us suffix in it. So nitrous and sulfurous, because there were nitrite and sulfite ions in those formulas. So acid nomenclature can be a little bit tricky, but hopefully with some practice, you'll be pretty good at it soon.